Okay, hey AP friends, we're going to talk about rotation today. This document is just a note guide that I created for you, and so a lot of it is just empty space we have to fill out, but it's going to be really good review because we have to go back and talk about all the linear things that we talked about at the beginning of the year and how that translates into something going round and round. So like a motor, a merry-go-round, a wheel, something that's rotating. So a couple of things first. We have to define our idea of an arc length. And this is just an area, a segment of the circle. It can be any piece. It can be a really, really tiny one. It can be a really, really big one. But we define an arc length using the letter S. And that's equal to the radius of the circle times the amount of rotation, delta theta. We use theta for an angle pretty often, and we're going to see that a lot here. A radian is just a unit of measurement. Someone way back when decided that 360 degrees would be a great way to break up a circle because that's how many days they thought it took the Earth to get around the sun. And so they used 360 and it just kind of stuck. But when we are talking about rotation, we're going to mainly use radians. And radians is a convenient measure when we think about it in terms of arc length. We know that going completely around a circle is 2 pi radians. And so we can relate 360 degrees to 2 pi radians. We also know that 1 revolution would be 2 pi radians, or 1 rotation would be 2 pi radians. We'll see that terminology pretty often. And so what really is a radian? Well, if we look at this equation here, if we say our amount of rotation is the arc length over the radius, and we've just taken this equation and solved for delta theta. If we take a string and we measure out the radius, so I have a string here, we measure the radius of the circle. We say, oh, it's about that long. And then we put that length of the radius and we lay it along the length of the circle. So basically we're saying when the radius equals the arc length, and if we plug it in here, we could say maybe my radius is 1 and my arc length is 1, we get an angle of 1. That's 1 radian. So when our arc length equals our radius, we have 1 radian. And that's just, side note, probably nothing that will ever be asked. We have to be able to do these conversions from 360 degrees equaling 2 pi radians. 1 revolution is 2 pi radian, or 1 rotation. But it's really handy to be able to convert these because AP Test likes to add a layer of difficulty by making you convert. So see if you can do those without looking at my answers, even though I'm showing them to you. Make yourself do it. Go ahead and stop or pause the video and do those problems first. All right, now that we're back, and this is kind of a lot that we have to talk about, but I'm going to go piece by piece. So on this side of our chart, we have our linear kinematic quantities. And so this is what we started talking about at the beginning of the year. If you remember, like week 1, we talked about displacement, and then we talked about velocity, and then we talked about acceleration, and then we talked about our uniform acceleration or uniform accelerated motion equations. So we're just going to start at the beginning. Displacement. This is how far we are from a starting point if we're talking about moving in a straight line. And it's measured in units of meters. We use the symbol delta x. And we can relate that to an angular or a rotational kinematic quantity. And we know that already. The amount of displacement when we're rotating on our angle up here, on our circle up here, is this angle, which we call delta theta. And so we call an angular displacement delta theta. It's measured in radians, and it's telling us how much we've rotated. And so how do we convert back and forth? Well, we know that already. We use our arc length. And so we could see this as S for arc length, or this would be the same as our linear quantity displacement. So we can say displacement is equal to R theta. And I've put a little radian down here so that we remember that our angle has to be in radians in order for this conversion to be true. Pretty much everything has to be in radians for these things to work out. So keep that in mind. So this is an interesting thing to think about, right? If we have some amount of rotation, if we look at my picture here, we are relating this arc length. If we were actually moving that circle and we looked at that arc length in relation to this piece here, that would be our linear quantity, right? We can imagine the amount of rotation of that wheel if this was point A and this was point B, rolling that linear distance. And so that's why we get to say our arc length or our displacement is equal to the radius times the amount of rotation. Okay, pretty straightforward. Next, we talked about velocity. We measure that in meters per second, and we had the equation velocity is a change in position over time, our displacement over time. Our angular velocity or our rotation is Greek symbol omega, kind of looks like a fancy curly W, and it's measured in radians per second. And how do we relate those? Well, you can notice this pattern if we know that our linear displacement is equal to a radius times our angular displacement. Well, then our tangential velocity or our linear velocity is equal to a radius times omega in radians, our angular velocity. This tangential piece just means if I had something sitting on the edge of my circle and all of a sudden it flew off my wheel, it would fly off tangentially or linearly to the circle. And so that's what this piece is in terms of this relationship, this conversion. Okay, next we talked about acceleration. We know it's measured in meters per second squared, and it's a change in velocity over time. Our angular acceleration is alpha. A lot of people like to call it a fish because it looks like a fish. And it's measured in radians per second squared. You see these patterns. They're pretty similar. We're just changing a linear distance to a rotational distance for our units there. And how do we convert back and forth? Well, our tangential acceleration or our linear acceleration is equal to r alpha in radians. And that's pretty straightforward, just like these guys. And you'll see these on the AP test, or at least typically they like to include this one, but not the other two. But if you know this one, you can easily jump to these two. All right. So next we talked about our uniform accelerated motion equations, and we said there are three of them. Our final velocity equals our initial velocity plus acceleration times time. Final velocity squared equals initial velocity squared plus 2 acceleration times change in displacement. Change in displacement is initial velocity times time plus 1/2 times acceleration times time squared. Those should look pretty familiar. We spent a lot of time on those. We can essentially translate what we know these variables to be into our rotational variables. So we know that our velocity is really, when we're talking about rotation, omega. So a final velocity is a final omega that equals an initial omega plus alpha times time. Okay, we can do it for this one. Our omega final squared is equal to our initial omega squared plus 2 times alpha, oops, can't see that, times delta theta. All right, see if you can do this last one without looking. Did you get it? All right, our change in angular displacement is equal to omega initial times time plus 1/2 alpha time squared. Woohoo! All right, so then I gave you some practice problems. The first thing is that everything has to be in radians. That's big. So make sure if you get anything that's in revolutions or rotations, we convert it first. Just like we did kinematics, and we told you there are 5 variables, and we have to write those 5 down and keep track of them, because if we know 3 things, we can use an equation to solve for the other 2. And so if we read this problem really quick, and it's going to help you out if you pause the video here and see what you can do. But I'm going to walk through this one and then let you try the others. So we know that a wheel is starting from rest. So its initial angular velocity, omega, is 0. It accelerates at 2.5 radians per second squared. That's alpha. That's our angular acceleration. And it's going for 7.3 seconds. All right, time. So our units are all good. They're in radians. We don't have to do any conversions. We just need an equation that has these three and lets us find a final omega, a final rotational speed. And that happens to be omega final equals omega initial plus alpha t. And then it's as simple as plugging it in, doing some math, and we come up with 18.25 radians per second. Now, if you put radians into any of these equations, you will get radians out. And so the units should match what we have on our table. Okay, not too bad, just kind of like we're doing it in a different language. All right, these next ones you should do yourself. Oops, sorry. So make yourself do these before you see what's going on. I'm going to give you the answer there. Actually, I didn't do the math, but I set it up for you. And then the next one, I'm going to go ahead and give you that as well. Check that out. And then finally, the last one, I forgot to give you a piece of information. And so it says, a variable speed electric drill motor turning at 100 revolutions per second is uniformly accelerated at 50 revolutions per second squared up to 200 revolutions per second. Add that piece in. I didn't give it to you, which means you don't have enough information to solve that problem. How many turns does it make in this process? Be careful because this is all revolutions, and we need to have it in radians. So make yourself do these and then come back and check and see if you got them.